The impossible architecture. For as long as humans have looked at the night sky, we have seen a boundary. A ceiling we were never meant to crack. But 300 miles above your head right now, a 450-ton masterpiece of titanium and aluminum is screaming through the vacuum at 17,500 miles per hour. It circles the entire planet every 90 minutes. This is the International Space Station, the most expensive, complex, and politically improbable structure ever conceived. Building it didn't just require a new kind of blueprint, it required a new kind of physics. On Earth, gravity is your foundation. In orbit, gravity is your enemy and your architect. You aren't building a house, you are building a pressurized vessel that must withstand the structural stress of being constantly pulled toward Earth while moving fast enough to perpetually miss it. This is the story of how 5 space agencies and 15 nations turned a void into a home. The modular miracle. The sheer logistics of the ISS are staggering. No rocket in existence could lift a structure the size of a football field into orbit. Instead, engineers had to design the station as a massive, high-tech Lego set. The first piece, the Russian Zarya module, launched in 1998. It was a self-contained power and propulsion unit. 2 weeks later, the Space Shuttle Endeavour met it in the dark, carrying the Unity node. Imagine the precision required. You have 2 massive objects, moving at 5 miles per second, attempting to connect with the tolerance of a few millimeters. If the docking latches didn't engage perfectly, the mission, and the billions of dollars invested, would be lost to the void. Over the next decade, 40 more missions followed. Each piece had to be independently functional yet capable of integrating into a singular, interconnected nervous system of power, data, and life support. Powering the great machine. The most striking visual feature of the ISS is its massive wings, the solar array wings. These aren't just panels, they are the power plant of the station. Stretching 240 feet across, they contain over 260,000 individual solar cells. But here is the extreme engineering challenge. As the station orbits, it moves from the blistering 250 degrees Fahrenheit of direct sunlight into the minus 250 degrees of Earth's shadow every 45 minutes. This thermal cycling would shatter normal materials. The arrays must constantly rotate to track the sun, guided by massive alpha joints that are masterpieces of mechanical engineering. These joints must provide a continuous flow of high-voltage electricity while rotating in a vacuum, where traditional lubricants would simply evaporate or freeze. Without this power, the station's batteries would drain in hours, the air scrubbers would stop, and the fortress in the sky would become a frozen tomb. The life support abyss. To stay alive on the ISS, you have to bring your own Earth with you. The Environmental Control and Life Support System, or ECLSS, is the most sophisticated recycling plant ever built. Every drop of moisture is precious. The station's water recovery system collects everything: humidity from the breath of the astronauts, the runoff from their occasional sponge baths, and yes, the urine. Through a multi-stage process of distillation and filtration, this wastewater is turned back into water that is arguably purer than what comes out of a tap in New York or London. Then there is the air. The oxygen generation system uses a process called electrolysis to split water molecules into hydrogen and oxygen. The hydrogen is vented into space, and the oxygen is pumped into the cabin. It is a closed-loop dance with chemistry. If the pumps fail, or the filters clog, the carbon dioxide exhaled by the crew becomes a silent, invisible poison within minutes. The engineering here doesn't just support life, it manufactures it. The invisible shield space is not empty. It is a shooting gallery. The ISS is constantly being peppered by space junk, remnants of old satellites and rocket stages, as well as natural micrometeoroids. At orbital speeds, a fragment the size of a pea carries the kinetic energy of a hand grenade. To defend against this, the ISS is wrapped in Whipple shielding. This isn't just a thick wall of metal, it's a series of layers. When a high-speed fragment hits the outer aluminum layer, it doesn't just pierce it, the impact energy is so high the fragment vaporizes into a cloud of plasma. That cloud is then caught and absorbed by inner layers of Nextel and Kevlar. It is a bulletproof vest for a city. Yet, the danger is constant. On several occasions, the crew has had to retreat to their Soyuz or Dragon lifeboats because a piece of debris was tracked too late to move the entire station out of the way. The human toll and mechanical wear. After 25 years in the most extreme environment known to man, the ISS is showing its age. Metal fatigue, radiation damage, and the constant stress of thermal expansion have created micro cracks in the Russian Zvezda module. Fixing a leak when your basement is a 300-mile drop requires a level of courage and technical ingenuity that defines the modern age. Astronauts perform extravehicular activities, or spacewalks, lasting up to 8 hours. They are encased in a pressurized suit that is essentially a person-shaped spacecraft. They work with bulky gloves on tiny, intricate bolts, knowing that a single tear in their suit or a broken tether means drifting away into the silence forever. This is where engineering meets the human spirit. We built a machine so complex that it requires constant, dangerous human intervention just to keep its heart beating. The final descent and the future of the International Space Station was never meant to last forever. Eventually, the cost of maintenance will outweigh the scientific return. By the end of this decade, the most expensive object ever built will be intentionally deorbited. It will plunge into the atmosphere, becoming a man-made meteor, eventually finding its final resting place in a spacecraft cemetery at Point Nemo in the South Pacific. But its legacy is permanent. It proved that we could live and work in the stars. It showed us that when we face the infinite pressure of the vacuum, our national borders become invisible. The engineering lessons learned on the ISS are the foundation for the lunar gateway and the eventual human footprints on Mars. Join us next time as we return to Earth to examine a terrestrial giant, the Three Gorges Dam. A structure so massive that its reservoir actually shifted the Earth's mass, lengthening our days. This is Engineering Extreme.